Lab 15, data hazards. Again, there are different scenarios that we can analyze, and there are two scenarios analyzed in this lab. Data hazards resolved by forwarding to the decode stage, and raw data hazards resolved in the commit stage using two additional arithmetic logic units, which we have not yet shown. If I go back to the figure for the SWERVH1 processor, we said that we have an arithmetic logic unit at the X1 stage, but then in the commit stage we only are showing these multiplexers that select between different results coming from different places, but nothing else. But this is only a simplified figure, and in the commit stage there are what Western Digital calls secondary ALUs in order to resolve some specific situations with data hazards. The thing is, let me explain it, although we won't analyze it, it's in the document, but let me at least explain when this happens. So when you have an arithmetic logic instruction that depends, one of its operands depends on the result of a previous instruction, which is, for example, a multiplication or a multi-cycle instruction, an instruction that needs several cycles to compute its result, you cannot forward the value until it's been computed. Let's say an addition that depends on the result of a multiplication. So you cannot receive the value through forwarding until this moment when it's being computed by the multiplication. But in that case, the add instruction would have to wait for some cycles. In order to avoid that loss of time, what they do is they include another ALU here that recomputes the operation on the correct results. So if there's an addition depending on the multiplication, it will be computed here at the commit stage using the correct value from the multiplication. I don't know if it's too fast for, I don't know if it's clear. I mean, all the details are in the document. This situation is illustrated with an example exactly of this situation that I've just described. And it shows how the secondary ALUs compute the operation in those cases. Okay? But here I'm only focusing on the other situation, data hazard resolved at the decode stage by forwarding. So this is the typical case explained in the books. Well, let's say that we have an add instruction computing an addition using T4, computing T4 plus T5 and writing the result to T4, and this T4 is used as an input operand to this add instruction. Remember that we have two ways, so this will be, let's say this will be in way 0, this will be in way 1 in the same cycle, and then this will be in way 0 again. So the solution used here to resolve that data hazard is to forward this value from this instruction to this instruction. Okay? Well, this is another way of showing this. This figure shows again that we are doing a forwarding of the result obtained for this instruction at the X1 stage to the decode instruction of this, to the decode stage of this instruction, and we have this figure showing what happens inside the processor. So we have the second add instruction, the add T3, T3, T4. Look, this in the program we have the addition of T4 plus T5, then the addition of T3 plus T4. So we have the second addition at the decode stage, the first addition at the X1 stage. So this result of the first addition is forwarded through the forwarding logic to the second add instruction, so that it can use the result obtained by this instruction instead of the result read from the register file. Okay, this is the typical data hazard example resolved with forwarding from a later stage to a previous stage. Okay. I didn't include here, but we also do a very later simulation where this can be observed in the processor. Okay, I didn't include it here due to time constraints, but you can see it in the document. We also explain how this is not a this is a black box here, but we also explain in one section of the document how this is implemented inside. It's a 10-to-1 multiplexer, because we can receive the value from 5 different stages, and given that there are 2 ways and hazards can be from one way to the other, we have 10 possible inputs for the forwarded data. Okay? But well, you can look at the details on your own later. Lab 16 is about control hazards and branch instructions. Let me go very quickly through this lab. Branch instructions compute the address of the next instruction to fetch at the X1 stage. So there are several cycles that would be lost if we don't do a prediction. And SWRE-VH1 includes 2 branch predictors. Very simply, branch predictor, which in fact is not a branch predictor. It always predicts branches as not taken, and it only it has to redirect the fetch when branches are taken. It has poor performance but no hardware cost. And well, it has a hardware cost because it has to redirect the execution. Okay? But it doesn't include a branch predictor. Instead, we can also use a G-share branch predictor, which offers a higher performance at the cost of extra hardware, which is the branch predictor itself. In this lab, we analyze both predictors, how they work with a given example. We enable each of them, and we see the results. You will see in the example that this one achieves a much better performance. And we also explain how the G-share branch predictor is implemented. Okay? And also, we analyze branch instructions that we haven't so far. So we analyze how branch instructions are computed in the SWRE-VH1 pipeline at the X1 stage. Okay? But again, we don't have time for more details. The lab is quite extensive. You can analyze later. I think we can do this when I finish with all the labs. So the idea is that you review, you take some time to review these labs, but let's finish explanations and then you can do this if you want. So lab 17 explains superscalar execution. This is a 2-way superscalar processor. Remember, a superscalar processor contains multiple copies of the data path hardware to execute multiple instructions simultaneously. The latency of executing a single instruction is the same as a scalar processor, but the processor can execute more instructions per cycle, improving its throughput. Ideally, we would obtain an IPC of 2, but unfortunately, actual programs exhibit performance improvements of only 1.3 to 1.5 when going to a 2-way processor. SwearVH1 does not include support for dynamic instruction scheduling. Someone was asking that earlier. With out-of-order execution, except for the non-blocking loads. However, as you've seen in the hands-on activity for Lab 14, you can statically reorder the code in order to exploit more efficiently the resources, including the two ways of the pipeline. We include this example to show the dual execution. Again, it's a useless example except for analyzing these highlighted instructions. It's interesting to mention here that we can enable or disable dual issue execution and many other features of the processor, okay, by just configuring one register. There is a table which explains which bits should be enabled or disabled in order to enable or disable the different features. So you can, for example, compare, or you can enable or disable pipeline execution, or the secondary ALUs that I was mentioning, or dual issue execution, or other features of the processor. That gives you many options to propose different exercises, analyzing codes, and enabling and disabling the different features. Here we are enabling and disabling dual issue execution in this program. So we first disable it, so it's like a single issue processor, and you can see that the 4 instructions arrive at the decode stage, but they only execute through the way 0. Here we can see the signals for way 0 and for way 1. You can see that way 1 is empty, it does nothing. We only execute the instructions through way 0, obtaining the results sequentially. Well, we also include this figure. And then we enable dual issue execution, and this is what you obtain. In this case, the two ways are being used, results are obtained in both ways, and written back to the register file in both ways through the two write ports available in the register file. You can also compare measurements with the performance counters in this case and the other to compare IPC and so forth. Lab 18 is a very interesting and different lab to the previous ones, where we add new features to the core. So we ask students to add different things. First, we ask them to add arithmetic logic instructions from the bit manipulation extension available in the RISC-V architecture. So you know RISC-V has different extensions, and this bit manipulation extension is not supported by SwearVH1. So we ask students to include a subset of the instructions available in this extension. And we explain how to do that with an example, step-by-step, guided example. And then we ask them to include other bit manipulation instructions and test them both in Verilator and on the board. Okay. Then we ask to include floating point instructions. This is something which is also not supported by SwearVH1, floating point instructions. So we ask them to add 3 floating point instructions: addition, multiplication, and division. And once they are working in the core, we ask them to use them to compute different algorithms, such as an example, we ask for a dot product and a bisection algorithm, which use floating point calculations. Obviously, you could ask your students to implement the floating point unit by themselves. In the lab, we point to a floating point, an open source floating point unit that they can include in their processor, but they have to include the support for those instructions. we also ask them to compare execution of these algorithms when using the new instructions and when using software emulation of floating point computations. And finally, we ask them to add a hardware counter, which is not, or an event, to be more precise, which is not included in the original core, which counts for the number of type instructions. Well, you can choose any other event that you want. The idea is to understand how to include a new hardware counter in the processor. No time for anything else, but you have all the details in the documentation. Well, the last two labs, Lab 19 and Lab 20, are about memory. Lab 19 is about instruction cache, analyzes the instruction cache implementation and use in SWERV-VH1. And then Lab 20 analyzes the two scratchpad memories, one for data, one for instructions, available in the processor. This is a figure showing the instruction cache available in this processor. You can see that it has 4 ways. Well, it's configurable. You can increase its size or decrease it. In this configuration, we have 64 sets. We have the replacement state for an least recently used replacement policy, which is the one implemented in SWERV. And well, we read in parallel the 4 ways, compare the tags with the address part of the corresponding to the tag, and in case of a match, we signal a hit and we select the block or the instructions from the iCatch. Otherwise, we signal a miss and we request the instructions to the external memory. Again, these are the real names for the signals that you can find in the core, and you can try to understand the Verilog implementation of this structure. And we also explain the replacement policy used in the processor. It is a binary tree pseudo LRU. It's not a real LRU, but an approximation to it. It uses 3 bits per set, and this is the way they are updated. And well, when a block replacement happens, this is the way to replace, depending on the state of the LRU. And when a hit takes place, this is the updating of the LRU state. Okay? Well, all this is explained in detail, and an example is included. Finally, in Lab 20, we analyze the instruction scratchpad memory, the data scratchpad memory. The instruction scratchpad memory is not enabled, but we explain how to enable it and use it in this lab. It has a specific memory region for it, which is this one. The external memory has this region, is mapped to these addresses. And the data scratchpad memory, this one is enabled in our configuration, and this is the address region used for it. Its latency is of 1 cycle, so it makes the processor not stall when data is accessed from there. And in this lab, we also do something with benchmarking. Specifically, we use 2 common benchmarks in embedded systems, CoreMark and Drystone. And we use hardware counters in order to measure their performance in SWERV. And this is the last hands-on activity that you'll do now. So we'll ask you to test the CoreMark benchmark without using compiler optimizations nor the DCCM, then to use the DCCM, and finally to use both the DCCM and the compiler optimizations, and you'll see how performance increases as you include each feature. Before you do the hands-on and you take a look at all these labs from 11 to 20, let me show you some future work that we are preparing and that we hope to release soon. So Robert already commented on some of this. We're working on a virtual development board called VITBO, and I'd like to show you a demo of this. It's not ready, but it's quite advanced. This is not available on the materials that you have because it's not been released yet. So this is a demo for the LED switches example. Let me first show you, and then I'll explain what we are doing. So I run this. So we have this image of the board, and in Verilator we are running the LED switches example in our SOC. So the LED switches example reads the switches and shows the value on the LEDs. So if we connect to the board, you can see the program working. You can invert the switches. Well, the light is not too clear, but I hope you can see that when I toggle the switch, the value of the LED is changed. Okay? So for now, we only have these two peripherals implemented. Sorry, these two, the switches and the LEDs. But we're working on including other peripherals, such as the 7-segment displays or even serial devices communicating through serial buses, in order to be able to run most of our labs in this simulation environment, okay, which is very useful in case you don't have a board or you want to work remotely or whatever. This is what we have for now. It's not still completely integrated in Platform I/O because we have to run manually the scripts and so. But, well, there are still things to do, but I wanted to show you the demo for you to have an idea of what we plan to release, hopefully, quite soon. More future work. We're working on a smaller core by Western Digital, EL2, which is a single-issue core for stages pipeline, and our intention would be to show all these labs working in that core. And one of the good things of this core is that it's much smaller and it fits in smaller FPGAs. So it fits in a basis 3, for example, which is much cheaper than the A7. But also, it's a simpler core that may be more suitable for teaching those labs analyzing the core internals. It's more easy in this core. And also, we are thinking of maybe using other cores from open hardware, but this is something that we have not decided yet. Also, we have support for other boards in mind. Basis 3 is already working. I was planning, but I think I won't. I have a basis 3 here. I was planning to show you a demo, but, well, it's simply a demo that shows things in the 7-segment displays and reads the switches. Well, it's ready, that part, but it's not been, not all labs have been ported, so we want to release it when we have all the labs ready. We are also thinking of using Intel FPGAs or other FPGAs too. And we'd also like to include something called Pipeline Viewer, which allows you to view the simulations in a more convenient way, because you can see for example, the dependencies, and you can see how maybe you're familiar with this. This is originally from Gen 5 simulator, and it has been ported to other processors, and specifically it has been already ported by a German professor to EL2. So we like to use it in RVfpga in order to improve the understanding of those example programs where we have